Hello and welcome to our paper. The title is Biologically Plausible Variation of Policy Gradient with Spiking Recurrent Winner-Take-All Networks. This paper lies in the intersection of reinforcement learning and spiking neural networks. In general reinforcement learning study, a deep neural network is used. This kind of research has been applied to many different tasks, including robot control, video games, and autonomous cars. There has been recently found some difficulties in achieving human-level performances, such as adaptability to different tasks, robustness to noises, and learning speed. For these difficulties, there has been a recent branch of reinforcement learning study that considers to imitate the structure and mechanisms of human brains. This branch of study generally considers to use a spiking neural network model to replace the traditional deep neural networks for representing the policy function. There are mainly three types of methods in this branch of study. The first type considers to transform a pre-trained deep neural network to a spiking neural network. The second type considers a certain kind of surrogate function to approximate the spiking activities of the neurons so that the traditional gradient-based backpropagation method can be applied to spiking neural networks. This paper belongs to the third type, which considers a certain kind of modulation of spike timing-dependent plasticity, which is a set of local learning rules. This type of method has the advantage of being biologically plausible. However, recent proposed methods generally rely on heuristic designs of the local learning rules and hyperparameters. This limits their generality to different tasks. In this paper, we consider the leaky integrate and fire neurons as the basis component of neural networks. The second line of equation on this slide represents the basic framework of spike timing-dependent plasticity. Here, the underlined parts represent the local signals of neural activities. The symbols W and A represent the variables which determine a certain learning rule. The third line of equation on this slide is the global reinforcement learning target. Here we consider the reinforce algorithm, so this target takes the form of a policy gradient. So the key problem is how can we establish the connection between the local learning rules and the global reinforcement learning target. In this paper, we mainly made two designs. The first design is a recurrent winner-take-all network. For the state input part, we consider a rate coding, that is to map the state elements to the range of 0 to 1. The network mainly consists of several winner-take-all circuits. There is one winner-take-all circuit that is considered to be the action circuit, which are used to output the actions to the reinforcement learning environment. The other winner-take-all circuits are considered to be hidden circuits. The connections starting from the state input to other circuits are considered to be unidirectional. The other connections, that is the connections between the winner-take-all circuits, are considered to be bidirectional. That is, the synaptic weights are shared between the neurons connected. For each winner-take-all circuit and at each spiking time step, we require that only one neuron fires in that circuit. In the following part, we will use the symbol V to represent the firing states of the neurons. For each winner-take-all circuit, this means a one-hot vector. We will use the symbol Q to represent the firing probabilities of the neurons. The second design is that we define the policy function pi with an energy function. Although the energy function here is linear and looks simple, the normalization operation makes it capable of representing complex functions. With these two designs, we need to derive the specific algorithm for our model. This consists of two parts, policy inference and policy optimization. For the policy inference part, recall that the target policy function involves a sum of probability values over all possible hidden neuron values. This is quite complex to do in practice. So we perform a mean field variational inference of this function. That is to approximate it with a series of productions of simple probability functions. By minimizing the KL divergence between the approximation and the target, we reach the equation 1 shown on this slide. This equation defines an iterative process for calculating the probability values Q. In practice, we can initialize the Q with some random numbers and use equation 1 iteratively until convergence, or for a certain number of steps. For this iterative process, we show that our RWT network with some simple settings can perform an equivalent process. This means that our network as a biological plausible model is suitable for performing the mean field policy inference in our setting. For the policy optimization part, we first derive the precise differential of the policy inference function. The results are shown here. For the definitions of the symbols, please refer to our main text. The results show that it requires the calculation of a pseudo-inverse of a certain matrix, which is quite complex and makes it infeasible in practice. Therefore, we derive a first-order approximation of the policy inference function differential, and the result is shown as the right equation here. Again, we show that with some simple assumptions and by citing the STDP rules according to the green equation, there is an equivalence between the STDP rule and the right equation. This means that these designed STDP rules can do the approximated policy optimization. Here is a sketch of the overall algorithm structure. You can find this table in our appendix. In our experiment, we used two tasks. The first is a reward-based MNIST classification task, and the second one is a classical gene inverted pendulum task. We consider three types of environment variations. Note that the variations are not added to the environment during training. They are added only during testing. The first two types are respectively input noises and network noises. The third type is environment variations in the inverted pendulum task. That is, we vary the length and the thicknesses of the pendulum during testing. We also consider several variations of our method. For the STDP window, we consider two options, double exponential and rectangle. We also consider to estimate the firing rate with some Gaussian noise added to the firing probability. The results on a MNIST dataset with input source noise and network Gaussian noise show that these three variations get similar performances. Since the third variation is more computationally efficient, we use this variation as the representative of our method. We also consider a shrinked version of our method in which the number of hidden neurons is reduced so that the total number of learnable parameters is equal or less than the other compared method. Here are the results. In the first part, we show that on a MNIST dataset, our method can achieve an accuracy close to the traditional ANN-based method. On the inverted pendulum task, we show that our method can achieve near optimal performances. Our main findings is about the robustness to noises. Here we show some of our results. For the full set of results, please refer to our appendix. The results show that there is no significant performance degradation after the shrink operation of our method. And based on this, our method achieves better robustness to multiple types of input noises and network noises in both the tasks we considered in our experiments. There is also an extra finding in the inverted pendulum task. As shown in the figures, our method achieves much better zero-shot adaptability to variations in both the thicknesses and the length of the pendulum. We also perform some visualizations of our method. The first result is SVPG tends to learn a more sparse networks than traditional multilayer perception. The second result is that the recurrent design in our network should contribute to the robustness to the input noises. The computation costs show that our method is relatively fast in the optimization part. Here is a brief summary of our paper. We propose SVPG, a speckling-based variational policy gradient method with RWTA network and reward-modulated HTTP. Current experimental results review its potential for solving high-dimensional reinforcement learning tasks and to have inherent robustness. At the end of this presentation, I would like to express my gratitude to the project and findings that support our work. This is the end of our presentation. Thanks for listening.